Hi everyone, welcome back to Dronacharya online classes. Today we are going to see electrolytic conductance. What is electrolytic conductance? As we know that the flow of electricity through a solution of electrolytes due to the migration of ions. When potential difference is applied between two electrodes. So let us consider an electrolyte solution. So this is an electrolyte solution. So here, so I am applying potential difference between these two electrodes. So here, so I am connecting these two electrodes to a battery. So here, a positive terminal and negative terminal. Okay. So here, if I pass the electricity to this solution through these electrodes, so the positive ions which are present in this solution will move towards the negative electrode. So this electrode can be act as a cathode. Okay, so here it can be act as a cathode, and negative ions which are present in this electrolyte solution will move towards the positive electrode. So this electrode will act as a anode. So here it is a anode. Okay. So now in the case of electrolytic conductance, so we are mainly talk about conductance instead. Okay. So what is meant by this conductance? Okay. So conductance is nothing but the ease with which ions can flow through an electrolytic solution. Here conductance means the ease with which ions can flow through an electrolyte solution. Okay, so here see it can also defined as the reciprocal of resistance. The reciprocal of resistance is also called as conductance. So this conductance can be denoted with the symbol that is C. So in sometimes it can also denoted with the help of G. So where C is equal to 1 by R. So here R is the resistance. Okay. So now what is a resistance? So what is meant by resistance? So the resistance of a conductor. So the resistance of a conductor is directly proportional to the length of the electrode and the area of the cross section of electrode. So let us consider an electrode. So here we have these two electrode plates. So these are the two electrode plates. So here, so these are the two electrode plates which are using to pass the electricity to the solution. So here, so this is a positive electrode and negative electrode. So the distance between these two electrode plates, so what we call as L. Okay, so the area of the cross section of these two electrodes, what we call as A. Okay, so the resistance of this conductor or this electrode is directly proportional to the length of the electrode. So it is nothing but the distance between the two electrodes. Okay, so these two plates is called as length. So this is a length of the two electrodes. So here, so these two electrode plates are separated with the length L. Okay, so this is the area of the cross section. So here the resistance is directly proportional to length of the electrode and the area inversely proportional to the area of the cross section, where R is equal to rho into L by A. So where rho is equal to rho is equal to specific resistance. Okay, so what is meant by specific resistance? So if the two electrode plates are separated with a length that is 1 centimeter and the area of the cross section is 1 centimeter cube. So here, if these two electrode plates are separated about 1 centimeter and the area of the cross section is 1 centimeter square. So 1 centimeter square. Okay, so the resistance of these electrode is equal to the specific resistance. It means the resistance offered by a specimen of 1 centimeter cube electrode or 1 centimeter cube conductor. So here the resistance can be defined as, so the resistance of a conductor is directly proportional to length of the conductor and inversely proportional to area of the cross section. Now here we are introducing a new term, so in the place of proportionality constant, so that is rho. So here rho is the specific resistance. So here specific resistance can be defined as the resistance of a specimen of 1 centimeter cube conductor. So here if I take 1 unit of conductor, so the resistance offered by that a specimen of that 1 centimeter cube conductor is called as specific resistance. Okay, now if I substitute the value of this R in the above equation, so as we know that C is equal to 1 by R, so conductance is equal to 1 by R. So here if I substitute the value of R in this equation, so I will get, so here C is equal to 1 by rho into A by L. So here 1 by rho, so this 1 by rho what we call as specific conductance, or it is also called as conductivity. Okay, so what is specific conductance? So it is a reciprocal of the specific resistance and it can be denoted. So here, so I will write this specific conductance here. So specific conductance. So it can be denoted with the help of the symbol that is kappa. So here it is kappa. Okay, so what is this specific conductance? So as we know that the conductance is equal to, so 1 by rho into A by L. So where 1 by rho, so which is a specific conductance, so C is equal to kappa into A by L. So where kappa is equal to C into L by A. Okay, so what is the definition of this specific conductance? Now let if the two electrode plates are separated with 1 centimeter and area of the cross section is 1 centimeter square. So now here, so this equation becomes C is equal to kappa. So it means the specific conductance of a electrolyte solution is the conductance offered by the all the ions present in the 1 centimeter cube area. So here in the case of specific conductance, so it is the conducting power of all ions present in the electrolyte solution which is in 1 centimeter cube area. Okay, so here the specific conductance means conductance offered by the all the ions present in the 1 centimeter cube electrolyte solution. So here, so this is the specific conductance. So this is the significance of specific conductance. So what is conductance? So conductance is nothing but the conducting power of all the ions present in the electrolyte solution. What is specific conductance? The conducting power of all the ions present in the 1 centimeter cube electrolyte solution. So here, so get in my point. So here the conductance offered by all the ions present in the 1 centimeter cube area. So here this is the specific conductance. Okay, so now let us derive the units of this conductance and specific conductance. So here, as we know that, so resistance, so the units of this resistance is ohm. So it can be denoted as ohm. Okay, so in the case of conductance, so here the reciprocal of the resistance, so it is nothing but ohm inverse. So ohm inverse. So ohm inverse is the units of conductance. Now specific conductance. As we know that, so specific conductance, that is kappa is equal to 1 by R into L by A. Okay, so here, so 1 by R is nothing but conductance, so it is kappa is equal to ohm inverse into centimeter by centimeter square. Okay, so here this square and centimeter will be cancelled out, so we get ohm inverse centimeter inverse. Okay, so we can also represent this one as ohm inverse meter inverse. Okay, so this conductance can also represent as a Siemens. Okay, so Siemens. Okay, so here, so Siemens into meter inverse or centimeter inverse. Okay, so this is CGS units. This is SI units. Okay, so this is about the conductance and specific conductance. So another term that is here, cell constant. So what is this cell constant? So it can be denoted with the help of G star. So it can be denoted with the letter G star. Okay, so where this G star is equal to by A. So here, so G star is equal to L by A. So it is the ratio of length of the electrode and area of the cross section is nothing but it is a cell constant. Okay, so here the units of this cell constant, that is, so L means so length, so that is measured in terms of centimeter. The units for length is centimeter and area of cross section is centimeter square. So here we get centimeter inverse. So this cell constant will be having units centimeter inverse. Okay, so here if you see this one, so here if you see this one, so here in the case of this specific conductance, so this specific conductance is depends upon this cell constant. So here kappa is equal to conductance into G star. So G star is the specific, G star is the cell constant. Okay, so it means specific conductance is depends upon the, so both conductance as well as the distance between two electrodes. So here the dimensions of the electrode, so it can simply dimensions of the electrode. Okay, so this is about the conductance, specific conductance and cell constants. Equivalent conductance. Equivalent conductance. So what is this equivalent conductance? So it can be denoted with the help of a lambda. Okay, so in some textbooks they are giving lambda V. Okay, so lambda V. Okay, so equivalent conductance. Okay, so what is this equivalent conductance? So equivalent conductance is a conductance offered by the all the ions present in the 1 gram equivalent electrolyte solution. So here the equivalent conductance is a conductance offered by the all ions present in a electrolyte solution containing 1 gram equivalent electrolyte. Okay, so here, so the equivalence conductance of an electrolyte solution is a conductance offered by the all the ions present in the electrolyte solution containing 1 gram equivalent electrolyte. Now let us consider an electrolyte solution. So here let us consider an electrolyte solution. So this is the electrolyte solution. So here we have electrolyte solution. So in this electrolyte solution we have 1 gram equivalent electrolyte. Okay, so 1 gram equivalent electrolyte. Okay, so here the volume of this electrolyte solution is V. So here V ml of electrolyte solution. So this is a electrolyte solution. Okay, so here, so this is the electrolyte solution. So here, if the volume of, so here let volume is equal to 1 centimeter cube. So here it is nothing but 1 cc or 1 ml. So here if the volume is equal to the 1 ml. Okay, so this 1 ml of electrolyte solution containing 1 gram equivalent electrolyte. So if I measure the conductance of this electrolyte solution, so here measured conductance, so here measured conductance is equal to the specific conductance. Okay, so here, so getting my point. So if the volume of this electrolyte solution is equal to the 1 ml, so here volume is 1 ml. So this 1 ml of electrolyte solution containing 1 gram equivalent electrolyte. So here, see if I measure the conductance of this 1 ml of electrolyte solution, so that conductance is equal to the specific conductance, that is kappa. So here, so what about the equivalence conductance? So here, so equivalence conductance is equal to the kappa, because here, so this 1 ml of solution containing 1 gram equivalent electrolyte. So here, since so the electrolyte solution which is containing 1 gram equivalent solution, so that can be equal to the equivalence conductance. So here, so this 1 ml of electrolyte solution containing 1 gram equivalent of electrolyte. So here, so the equivalence conductance is equal to the specific conductance. So here lambda is equal to kappa. Okay, so if the volume of electrolyte solution, so if volume of electrolyte solution is equal to the 4 ml. So the measured conductance is equal to the 4 into kappa, because here this 4 ml of electrolyte solution containing 1 gram equivalent electrolyte. So the total conductance of this electrolyte solution is equal to the equivalence conductance. That is equal to 4 into kappa or kappa into 4. So lambda V is equal to kappa into 4. So if volume is equal to V ml, so in that case, so this equivalence conductance, that is lambda V, is equal to kappa into V. So kappa into V. Okay, so here what are the units of this equivalence conductance? Okay, so as we know that the units of this specific conductance, so here lambda V is equal to, the units of specific conductance is ohm inverse and centimeter inverse. Okay, so here V, so the volume of solution containing 1 gram equivalent electrolyte. So V means volume of solution containing 1 gram equivalent electrolyte. So here, so volume, so centimeter cube, and equivalent inverse. So equivalent inverse. So here, so this inverse and cube will be cancelled and we get, so lambda V is equal to ohm inverse centimeter square equivalent inverse. So these are the units of this equivalence conductance. Okay, so ohm inverse centimeter square equivalent inverse. So it can also represent as lambda V is equal to ohm inverse meter square equivalent inverse. Okay, so this is the units of this equivalence conductance. Now let us derive the relation between equivalence conductance, that is lambda V, and concentration of electrolyte solution. Okay, concentration of electrolyte solution. Okay, so here in this case, so as we know that lambda V is equal to kappa into volume. Okay, so kappa is the specific conductance. So here in the case of this, this is the electrolyte solution. So here V ml and here we have 1 gram equivalent electrolyte. So 1 gram equivalent electrolyte. Okay, so now this is the electrolyte solution. Now here, as we know that, so normality is equal to, so here since it is a equivalence conductance, that's why I am assuming concentration in terms of normality. So if it is molar conductivity, we can assume as a molarity. Okay, so here it is normality. So normality is equal to weight of the solute by gram equivalent weight of the solute into 1000 by volume. Okay, so here weight by gram equivalent weight, it is nothing but number of gram equivalents. So here normality is equal to number of gram equivalents into 1000 by volume. Okay, so here number of gram equivalents is 1. So here we are taking only 1 gram equivalent. So here we have normality is equal to 1 into 1000 by V. So here if I take this V into this side, so here V is equal to 1000 by N. Okay, so if I substitute the value of this V in the above equation, so we get, so lambda V is equal to kappa into 1000 by N. Okay, so where N is the normality of the electrolyte solution. So so it can be represented as lambda V is equal to kappa into 1000 by C. So C is the concentration of the electrolyte solution. So here this is about the relationship between the concentration of the electrolyte solution and equivalence conductance. Okay, so is it clear? So now let us see molar conductance. So let us see molar conductance. So it can be denoted with the lambda m. So some textbooks they are giving mu c. Okay, so whatever may be the symbol, so here, so it can be denoted with the help of lambda m or mu c. So molar conductance, what is meant by molar conductance? The conductance offered by the conductance offered by the all ions present in a electrolyte solution containing 1 mole electrolyte. So here the conducting power of all the ions present in the electrolyte solution containing 1 mole electrolyte. Okay, so let us consider again, this is the electrolyte solution, so which is containing 1 mole electrolyte. So 1 mole electrolyte, so the volume of this electrolyte solution, so here volume is equal to VML. Okay, so this is electrolyte solution, So here if the volume, so let volume is equal to 1 ml. So 1 ml. So if I measure the conductance of this 1 ml electrolyte solution, so that measured conductance is equal to specific conductance, since this 1 ml of electrolyte solution containing 1 mole electrolyte. So here, so that 1 mole electrolyte, the conductance of that 1 mole electrolyte is nothing but it is a molar conductance. So here molar conductance is equal to the specific conductance. So here lambda m is equal to kappa. Okay, so if volume is equal to 4 ml, so lambda m is equal to kappa into 4. So if volume is equal to VML, so lambda m is equal to kappa into V. Okay, so this is the specific conductance into volume, so that is equal to the molar conductance. Okay, So now let us derive the units of this molar conductance. Okay, so as we know that, so lambda m is equal to, we know that specific conductance, that is ohm inverse, centimeter inverse, and V means, so here the volume of the solution containing 1 mole electrolyte, so here, so it is centimeter cube mole inverse. So here this cube and inverse will be cancelled out. So here lambda m is equal to ohm inverse centimeter square mole inverse. Okay, so this is the units of this molar conductance. Okay, so lambda m is equal to ohm inverse meter square mole inverse. So this is CGS and this is SI matrix. Okay, so these are the units of this molar conductance. Now let us see the relationship between this molar conductance and the concentration. Okay, so here, so again I am assuming an electrolyte solution, so which is containing 1 mole electrolyte. So here volume is VML. Okay, so we know that lambda m or mu c is equal to kappa into volume. So here volume, so let us derive the expression for volume. So we know that molarity is equal to weight by gram molecular weight into 1000 by volume. Okay, so here weight by gram molecular weight is nothing but number of moles. So here number of moles into 1000 by volume. Okay, so number of moles is 1. So in that case molarity is equal to 1 into 1000 by V, where V is equal to 1000 by m. Okay, so mu c is equal to kappa into 1000 by m. So this is the relationship between the concentration of electrolyte solution and molar conductance. So here m is the molarity of the electrolyte solution. So this is about the equivalence conductance and molar conductance. So I hope so it is clear about this conductance and specific conductance and molar conductance. So please like, share and subscribe my channel and tap the bell icon for more updates. So we will see you in our next class. So I hope you are enjoyed this session. So thank you for watching. Have a nice day.